in this case, it will be myself. Usually the chair is also the most expert in the panel respect to your proposal. And in this case, it's also not the case because I come from the P4 domain. Now, said that, what we are going to do is to reproduce also the minutes that Toma and Monica had for their interviews. Toma had 10 minutes of presentation, followed by 15 minutes of questions. Monica had 5 minutes of presentation, followed by 20 minutes of questions. Now we go on with the mock. Toma, the floor is yours. You can, now I will stop sharing my presentation and the floor is yours.
Thank you very much. Thank you for the invitation. My name is Thomas Susi from the University of Vienna, and it's my pleasure to present my ERC starting grant project ATMEN to you today. As you may know, electron microscopes can be used for imaging the atomic structure of materials, but what we've discovered in the last few years is that the focused electron irradiation in a scanning transmission electron microscope in fact can manipulate individual atoms. Of course, the chemical structure of materials is a very important question for material science. In fact, the exact arrangement of the specific elements in a material fully determines its properties. And there are two broad ways to modify this structure. One is kind of from the bottom up to self-assemble smaller units, which I would call kind of a chemical approach. And the other way is to come from the top down to directly assemble these structures using some larger instrumentation, and this I would label as a physics-based approach. In fact, this top-down approach has been used for almost 2 decades, namely the scanning tunneling microscope, to directly manipulate individual atoms on surfaces into various structures. And this is a technique that still provides very useful insight. For example, very recently, this type of molecule of triangulene that couldn't be made in otherwise by chemical means, 2 hydrogen atoms were cleaved away with very precise control. The way these techniques work is that you have an atomically sharp tip that approaches the surface, and it is able to pick up atoms from the surface and deposit them to another position in a very, very fine level of control. The crucial disadvantage of these tip-based methods, apart from the fact that you have a physical tip approaching a surface, so it only works from the surfaces, is the fact that there's an energy regime that has to be fulfilled. So the barrier to move the atoms needs to be smaller than the barrier of removing atoms from the tip, because otherwise you will degrade your tip and you won't be able to manipulate anything. And that unfortunately means that the surface atoms have to be relatively weakly bound on the surface for this to be possible, and that means that structures that you create are unstable above cryogenic temperatures. So if you take it out of your cryostat, all of this manipulation is lost. Now we've discovered a new approach to use electron impacts to do this manipulation, and the physics of electron scattering can be summarized in 2 types of conservation laws: energy and momentum conservation. And the energies we use in electron microscopy are tens of kiloelectron volts, but in fact, momentum conservation limits how much energy can be transferred in a momentum conserving collision. And these dynamics that may happen, damage or other type of dynamics, happen on a very fast time scale. So therefore, modeling is actually really vital for understanding these processes. And the kind of central finding of the ATMEN project and the central attractiveness of it is that the electron impacts can transfer 10 electron volts or even more to atoms in the structure, and therefore any manipulation or any changes you make to the structure are far beyond room temperature thermal stability limits. So if we are able to manipulate structures with the electron beams, they will be stable outside of cryogenic temperatures. To demonstrate this, and in fact the material where we discovered this to be possible is graphene, which is one layer of graphite, a 2-dimensional material, which has outstanding mechanical and electronic properties that really makes this ideal as a test bed and a demonstration for the ability to manipulate its structure. And the purpose of our project is to use a focused electron beam, which is really focused to the size of a single atom to achieve atomic resolution imaging. And we have various detectors to form images of the structure. And due to the fact that the scattering is proportional to the atomic number of elements in your structure, we have direct chemical contrast in this technique, so we can tell apart from silicon from carbon or even nitrogen from carbon, and this is, of course, very convenient. The way we discovered that there is this possibility happened entirely by accident. So a few years ago, we were imaging, in fact, silicon substitutional dopant atoms in graphene, and we observed that they sometimes seem to jump from one lattice site to the other. This is not damage because no atoms have been lost from the structure. In fact, we've only seen a silicon atom move by one lattice site. We then turned to density functional theory-based molecular dynamics modeling to simulate the process around this. And as it turns out, there is a certain window of energies, a certain window of probabilities, whereby an electron impact on one of the carbon atoms neighboring the silicon causes it to jump over the silicon atom, kind of like a little checkers game. And this, we believe, is the process by which the silicon atom then moves lattice sites. And crucially here, it's not the silicon atom itself that is impacted by the electron beam. It has a very high mass, so it is less affected by it in a momentum conservation collision, but it is one of the three neighboring carbon atoms. And in fact, I mentioned that our electron beam is the size of a single atom, and we control it very precisely, and we can in fact place it on one of the three neighbors and thereby choose the direction to which the silicon atom will jump. This was in the beginning just a theoretical proposal, but right around the time of the proposal, we managed to demonstrate this control for the first time. And here you see a series of images where the silicon atom that we manipulate is circled with the dashed circle, and the little dot indicates where we drag the cursor that directs the electron beam. And so we always take an image, irradiate one atomic site, take an image, irradiate another site, and therefore iteratively move this silicon atom through the lattice. This is quite laborious to do with manual manipulation, and a big part of my project is the effort to automate this. And in fact, we already have some ideas, which are described in the proposal, by which we can use the detector signal, which, as I mentioned, is proportional to the atomic number. And so while we are irradiating one of the carbon atoms, if the silicon in fact jumps there, that signal will jump up, and we can use this as a feedback signal to automatically then trigger another frame and know that the manipulation has happened. And this is very easy with modern computerized electron microscopes that are fully controlled, and in fact we use open source Python software to drive our microscope. The goal of the project is to implant different kinds of dopant atoms into the lattice using low energy ion implantation, and then use automated imaging and computer vision to identify where the dopant atoms are, define a target pattern to move the atoms to, and then automatically direct the radiation iteratively to move the atoms to a desired location, which can then be again verified by imaging. The panel 4 here is an accidental configuration. We've not yet managed to manipulate this. There are many possibilities where this could lead. Similarly, from scanning tunneling microscopy, these types of quantum coral structures, which will look a little bit different in the case of atoms in the lattice rather than atoms on the surface. We also theorize that the placement of the atom itself could be a bit. So if it's in the top position or the bottom position, this could be 0 or 1. And in fact, this would have some of the highest storage densities in any known storage media. There's also other properties such as plasmons that could be quite interesting if we can create these structures in a controlled manner. We've already shown this manipulation for silicon. Boron and nitrogen have been noticed to move. We've observed it together with collaborators. Manipulation has not been done purposefully. There's also phosphorus dopants that are very interesting, and it seems by theoretical simulations that manipulation should also be possible there. So there's a wide range of different kinds of dopants that we hope to manipulate within the project. So this is all based on the work by myself and my collaborators over the past 5 years in these several publications. And in the ERC project duration, we have two types of kind of streams of work: modeling to understand the mechanisms, which use some of the machine learning techniques that have very recently become available. And of course, a large amount of experimentation to prepare the samples, to automate the manipulations, and then make this into potentially these larger scale structures and evaluating their properties. And we hope that STEM, scanning transmission electron microscopy, will be a practical tool for single atom manipulation. We will open source all of the code and all of the data. And there are also tantalizing hints that this technique could further work in 3 dimensions, where things are more complicated because we're always looking at projected dimensions, projected images, and therefore starting in 2D will be a good way to launch this field. With that, I'm very open to hear any questions you may have. Thank you.
Thank you very much. And congratulations again for having passed to this important step in the process of the ERC. And I would like also to note that it's promising that you have already shown many proof of concepts for your project. Now, with the panel, we're going to, let's say, ask you to address some of the concerns from the reviewers and also some of our personal questions. So my first doubt that comes also from the reviewer's point of view is you mentioned that it might be difficult to prevent the drifting of the beam in the proposal. And it's also noted that even the sample might be drifting. And how this will affect the possibility to extend then the experiment to a very high number of atoms.
Yes, indeed. So any microscope will drift. And in fact, the microscope we are using is from the company Neon, which has an ultra-stable sample stage. And I believe that at the current stage of development, this is the only instrument where this will be feasible to demonstrate. And it has drift rates of around 1 angstrom per minute, which is mind-boggling if you think about it. This is a macroscopic sample that drifts by 1 angstrom. And so
okay, thank you
it
so
should
much.
not be a full showstopper, and we have ways of mitigating that going forwards.
Thank you. And concerning always technical limits, how will you prevent the graphene lattice to be damaged by the beam?
Yeah, so this electron scattering energy transfer is a stochastic process, and so there's always a probability for a specific energy transfer. What we've shown by simulations already, some preliminary results, is that if we lower the primary beam energy, we can mitigate damage more than we mitigate the rate of these jumps to happen. So by tuning the primary beam energy, which again with the ion microscopes is very easy, we will be able to slow down everything, but we slow down damage more than we slow down the actual manipulation. And with automation and computer vision, we can also work with much lower doses than a human operator would need. These neural networks are very good with very noisy images.
Thank you. And instead, how will you detach the graphene sheet from the TEM grid?
We don't. So at this point, the graphene sits on the TEM grid, all the manipulation, implantation, everything happens. And in fact, in Vienna, there's a unique infrastructure that we're building that will allow us to do the implantation and the manipulation in the same vacuum system, which is a big reason why the Vienna laboratory is ideal for the proposed work. Further applications, of course, we'd have to think of device geometries, for example, but there are in situ electrical measurement setups and various setups that you can do within the electron microscope. So for the time being, we'd work with TM compatible samples only.
And the last question on my side, how will you test the performance of the memory?
Yes, so the memory is just a proposal for a small scale demonstration. So we are not proposing that this is going to be in your computer chips anytime soon. We'd like to reach 9 bits, maybe 27 bits if all goes well. And we just show that we are able to have the density that we theorize based on the simulation, and that we are controllably able to flip these bits read and write speeds are going to be very slow, at least for the initial demonstration. So this is really just a proof of concept. It's not really central to the grant. It's just one avenue that we hope to investigate.
Thank you very much. I open the floor for other questions. Maybe by raise of hands. Okay, Peter.
Thank you. I have a question related to the graphene defects. You already mentioned that lowering the dose, that knockout defects can be avoided. It's good, but what about the intrinsic defects of the graphene sample? And we know that any kind of not knockout defects, but for example, stone walls defects or other defects creation can be occur during this irradiation. And most importantly, in a heteroatom assembly, will the graphene defects formation behave differently compared to a individual heteroatom geometry? So the defects.
Yes, those are very good questions. So what is really vital for this technique, at least in the initial stage, is that we work at a primary beam energy of 60 kilovolts or plus minus 5. We can tune it. And at 60 kilovolts, graphene lattice does not get any defects. It doesn't get stone wells, bond rotations. We've quantified this by others and myself. It is basically totally impervious to damage, and this makes it really the ideal substrate. So in other materials, it might not be possible to mitigate the damage completely. When you have a heteroatom, of course, that is a weak link in the structure, and that's what we need to be able to do the manipulation. And when you build these larger structures up, that's why I have such a big part of the project devoted to modeling, because we do not want to just try to do this and notice that we fail. We want to create these also machine learning based potentials by which we can simulate these dynamics in much bigger assemblies and actually computationally study how close we can bring two atoms, for example, before the structure becomes irradiation unstable. So these are open questions, but I think the project has a very good prospects of figuring this out in an effective way, and then we'll find the limitations during the work, and then we'll try to do the structures in practice that appear to be possible.
Okay, but it means that you don't have any preliminary calculation like on the quantum corrals that about this.
So the structure that I showed you actually is relaxed with DFT. So on a static energetic basis, that is a stable structure. It probably is too dense because you can see it's quite corrugated, and probably at that point, irradiation stability would be a bigger concern. The dynamical calculations are 100 or 1,000 times more expensive, and that's why we need these neural network potentials to be able to do this in practice for the larger structures.
Okay, thank you.
Thank you, Peter. And then I see Gianvito and then Mihaly.
Okay, thank you. I would like to go again on this part of the calculation. So the proposal contains an experimental part and a modeling part, and you mentioned that the modeling is essential to the success of the project, and in particular, you're going to use artificial neural network. Can you give more details about the exact modeling approach that you will be using?
Yes, so this has, as we already all know, there's a lot of hype around artificial intelligence and machine learning, but in fact, the two approaches to machine learning that we propose to use in the project have already proven themselves. So a computer vision of noisy images, this is what neural networks were basically developed for. In terms of the interatomic potentials, there's already very good work whereby you use small DFT simulations with various displacements, maybe small molecular dynamics runs to sample a lot of different geometries. And from each of those geometries, you get a set of positions and forces and energies. And based on those, the neural network architectures, these have been already shown by Baylor, for example, as I cite in the proposal, is able to create an interatomic potential that essentially has the DFT accuracy, but runs about 10 to 100,000 times faster. So this is relatively new in material science now in 2017, but it really feels that this is going to be a very promising application of these machine learning techniques.
Okay, but I still miss, okay, sorry if I have just a final question.
Yes.
I still miss some details about the modeling. For example, how can modeling guide the selection of the accelerating voltage in the proposal?
And a short answer, please.
Yeah, so we set up a structure, we relax it with density functional theory. There are details in the proposal on the technical details of that. And then we run a molecular dynamics simulation by which we give one of the atoms a kick, The electron impact happens in such a small time scale that basically this is a good model for it. And then we follow the evolution of the atom that's been impacted with different starting energies. And
okay, it's clear.
by changing
Thank
the
you.
energy, we find the threshold where something happens.
Thank you. Now, give a restriction of time. We have 4 short questions for short answers from Mihaili, Sara, Lynn, Ina, one after the other.
Okay, thank you very much. I have a technical question for the experimental part. So you image your graphene with the heteroatom on it, and then you manipulate it. You place the beam on the bond that you want to break, and then you again take an image, and then maybe you do an EELS spectrum from the single atom. For these 3 different things, you probably have to set up the microscope beam in different ways. Can you still be sure that you are looking at the same atom with EELS once you did all these changes? Or maybe you don't have to reset it, I don't know. But I'm very interested.
Yeah, so scan, normal imaging is a scan, the beam is scanned, then you stop the beam and we get a cursor on the screen that we just drag to where we want the static irradiation to be.
And you don't have to change anything, right?
No. This is exactly the same beam parameters, lens parameters, everything. Okay. And also the very low drift is important, that we know that we don't move very far and confuse which atom we're looking at.
Okay. And then for the EELS?
In the case of EELS, we can in fact do the annular dark field imaging and EELS at the same time. So we can, when we place the beam on an atom, we just start acquisition on the EELS detector and acquire the spectrum. So it's very easy to do all of this without complicated changes of settings.
Okay, thank you. I'm convinced.
Thank you, Mihaili. Sara?
Yeah, so regarding the heteroatom platform, so what are the figure of merit that you're going to consider for the different atoms?
If you mean in terms of applications or like plasmons or memories, or what do you mean?
So why to consider this wide range of atoms?
Yes, some atoms have a different valence than graphene. So silicon works, but has a valence of 4 like graphene, so it doesn't electronically dope graphene, whereas nitrogen would be an N-type dope, and then boron would be a P-type dope, and phosphorus also N-type. So we hope they will be able to locally modify the electronic structure of graphene lattice. And just to see in which kinds of dopant atoms this is in fact possible, and we're not here to really do applications, we're really here to demonstrate this is possible and explore the limits of this feasibility.
Thank you, Lynn.
Thank you. I have a practical question for you. So I think it's clear from your proposal and from what you just said that you have the expertise both in the experiments and on the computational side. But having the experience and expertise yourself and basically supervising students that are supposed to do both things, those are 2 different things. Can you say a little bit about what your strategy is going to be? How are you going to keep up with developments on both sides? How are you going to supervise students?
Yeah, indeed. So the plan is to have 2 postdocs. And so the idea there would be that the postdocs are the ones who will actually be able to keep up with the latest developments and have the specific expertise. In fact, I've done my career half electron microscopy, half density functional theory. So I'm kind of ideally placed to do these simulations. And I've done both the experiment and the simulation to this day myself. So at least the things that we propose to do right now, those will be possible. For the machine learning, this is something I need to hire people who are expert on this. And that will be, of course, something we need to find good candidates. And I hope the ERC grant will allow that to happen.
Thank you. Ina, last question. We cannot hear you, Ina.
Now, I had to click on it several times for it to activate. I'm sorry. So my question is a little bit less scientific, but more on the impact of your research on the scientific field. Can you comment on that?
Well, the possibility to manipulate atoms has been something that has inspired nanotechnology for many decades, and scanning tunneling microscope and to some degree atomic force microscope have produced hundreds, if not thousands, of groundbreaking studies when these manipulated structures have been created on these surfaces. And should this be possible in the electron microscope for covalently bound atoms that are cryogenically or thermally stable and even air stable? That opens up all sorts of new possibilities for these manipulated structures. You could manipulate something, take it out from the microscope, put it into a measurement setup or some device prototype. And so I think it will just enable a lot of research that currently really isn't possible. Ultimately, what we want to do is we want to demonstrate and establish a platform, the code, the methods, and make this available for the research community, and then we'll see what people make of it. That's kind of what we hope to do. We want to enable as many people to do these experiments in the future.
Thank you. So now normally you would be thanked for your time and kicked out of the room. But now, before we pass to the next candidate, we would like to use this opportunity to ask a bit your impression, maybe some tips and tricks to share in 2 minutes to 3 minutes for people that are in the audience.
Yeah, short answers, really important. I was probably going a little bit too long. It's been a while since I gave this talk, so really try to answer as shortly as possible. Usually the panel members really want you to succeed, and they want to address the questions that referees, for example, had. They will not tell you, though. I think you broke character there a little bit. So they would not tell you which question is coming from referees and which is coming from the panel members. But there may be a very critical question asked by somebody who is actually a champion of your project and is coming from a referee, and he wants you to be able to address that. And there may be several. And so if you spend too long answering, you won't give the panel the chance to give you the chance to explain. And so that's really hard because you're passionate and you know your topic. But yeah, that's the main tip. Keep it really to the point and short. Panel members will ask more if it's not sufficient, but usually you tend to talk too long. And I probably did a bit of that.
Thank you so much, Toma. Thank you very much. And now we pass to the second interview of the day. So we have Monica Morales-Masis from University of Twente. So Monica, now we start with the mock. Let me congratulate you for having passed to this very important step on the interview. And now you can share your slides and start your presentation. 5 minutes.
Okay, can you see it before I start?
Yes.
Okay, thank you. So thank you for the opportunity to present my project CREATE. I'm Monica Morales-Masis, and it's a great pleasure to show you CREATE. So CREATE is about a new method to basically propose to solve the challenges of hybrid material thin film growth. The key feature of my project is the smart decoupling of the deposition of organic and inorganic components using different laser sources. But why do we need a new method to create hybrid organic-inorganic materials? We can look at the case of hybrid metal halide perovskites. These materials have been a game changer in optoelectronics. We have seen records of laser efficiencies, record for luminescence, and also unprecedented X-ray sensitivity. These materials are made of organic and inorganic components, right? But there is still a lot of challenges in these materials, regardless of these record efficiencies. For example, the materials are highly unstable. Mainly, one of the reasons is the very low formation energies. The best performances are still based on lead-containing materials. And in a field that has been basically running to get the most efficiency solar cells, the control growth of these materials has been highly overlooked. And this is what we are tackling with CREATE. I cannot change the slide. So the CREATE idea is about a pulse dual laser deposition. As I said, the key feature of this method is to decouple the deposition of the organic and inorganic components by making full thin films in a single substrate. The goal is divided in 3 different parts. The first goal is to basically demonstrate the method. So we want to show that we can do stoichiometric growth of hybrid organic and inorganic materials by using laser sources. The second part of the project is to demonstrate the formation of very complex compositions where we have different organic components and different inorganic components like different halides and so on. So to go to the impact on full versatility in terms of composition. And finally, the third part of the project is to reach ultimate control on thin film growth, where we want to demonstrate that by using laser sources, also different frequencies, we can also develop the epitaxial growth of these hybrid materials. And not only that, go to even more complex structures like large molecules and make layered materials. And the question is all this feasible? So since I started at the University of Twente less than a year ago, we have started to see we can make these kind of targets, and we can show that in vacuum we can keep stable a full organic target source, or also a full inorganic target that is basically in the solid state. This is just a first demonstration of the project that brings us to basically first demonstration of the project that says, okay, it is actually feasible to do this possibility. And okay, I actually missed one slide, sorry for that, because I went too fast, but I am basically the right PI for this project. I have been working on material science for many years, also in the synthesis of thin film growth and optoelectronics, all these by working in different institutes in the world. Now I'm at the University of Twente, and I can go from the synthesis of material to devices. And all this allows me to now take the next step to go to hybrid materials for the breakthrough in hybrid thin film growth. I am the right institution where I have the unique expertise on post-laser deposition. So this university has the highest amount of PLDs basically in the Netherlands, and also the right team to make this possible. And I also have the right network to also take the impact of the project further. All this places me in the leading position to craft and create complex hybrid materials with a unique deposition system, offering decisive improvement in future optoelectronics. And with this, thank you for your attention. I'm happy to answer your questions.
Thank you very much. Now I open the floor for questions, and I would like to start by first noting how promising is that you've already shown your many proof of principles. But then one question would be, so your proof of principle and film deposition trials have been carried out only for organic materials. So how do you address the fact that there is still a very high risk associated to quality and stability of hybrid film?
Yeah, so maybe if I can repeat your question. Your question is about the stability of the material related to the thin film quality?
Yes.
Yeah, so they are actually highly interlinked, because as we know, if we make a thin film that is polycrystalline, for example, you have a lot of grain boundaries. And in the case of solution process, there are a lot of challenges regarding the solvent that you use, but also the trapping of solvents. So once you grow these materials in the hot plate, these traps are actually defects that stay in your film. And over time, they try to leave the sample, and this leads to high degradation. So what we are proposing is a method that is fully dry, first of all. So we are not using solvents. And the idea is to control the growth such that you can, first of all, not have, for example, less grain boundaries, but also highly oriented film. So you can really control the orientation and not have the solvent that can be, leading to future degradations. And of course, these materials are highly complex in composition. So that means we need to make sure that there is a nicely uniform composition distribution in the films. And this is what we are trying to tackle here.
Thank you. One question is also about, it sounds very difficult what you propose, because you want to combine two different solid targets in the same chamber, one at room temperature, the other one in cryogenic conditions. How you will do that?
Yeah, so this is this idea, the creativity here is actually on combining two known methods. So the method of UV laser is actually demonstrated, it's called pulse laser deposition, and the infrared laser with a frozen target is called MAPLE system. So it's actually demonstrated. Here the challenge is to decouple the temperature of the two substrates, and this is basically engineering. So if the ERC allows, we are going to develop a method that is custom made. So we will design the system, work with the company that helps us design the vacuum chamber with the right temperature settings, and also isolating both sources. This is a proof of concept, so it is a complex system, and that's why I believe it's also really exciting, because it will lead to a lot of possibilities in terms of thin film growth.
Thank you so much. My last question is that you propose to fabricate these solar cells through various collaborations, but how you do prevent the oxidation during the transport between all the different locations?
Oh yeah, this is also, I mean, we have been doing this already. So we use vacuum, very, very small chambers that are, I mean, basically we put it inside the glove box, we fill it's all filled with nitrogen. We don't need to be in vacuum. So then the samples are translated always in tiny chambers. And we have some preliminary results there where we can make some material, send back and forth, and still make some nice solar cells.
Thank you so much. Now I open the floor for questions, and in list we have Giovanna, Sara, and Nina. We start with Giovanna.
Thank you very much for a very interesting overview. My question goes along the lines of your attempt to really compete with very low-cost solution processing methods. How do you think the vacuum-based techniques will be able to compete in that regard?
Yeah, that's an excellent point. So we don't compete in terms of cost. I think that's I think all of the methods that we have nowadays, they have benefits and no benefits. I think solution process will be used in roll-to-roll processing, and we already see it. However, there are still challenges that we cannot overcome with solution process. And we are proposing this to tackle all these other challenges. For example, when you go for very highly, texture structures, it's very difficult to have conformal growth. So if we can show conformal growth, that's already a big advantage. So we are tackling all these other challenges from the other techniques.
So in this process, one of the targets that you emphasize are lead-free systems, which could be to an extent incompatible with these, again, vacuum processing techniques. How will you mitigate this risk?
Yeah, so we are proposing lead-free. The idea here is to go again with this full versatility we are proposing with Create. Here the goal is independent. So we can, if a theoretician come and tell me we need this compound with like 10 different elements, we can say we can do it from our target and our laser. So the idea is the full versatility. And that means also that we can go with very highly volatile elements, bismuth, for example, very heavy elements, and still do this stoichiometric transfer. So I don't see the challenge there. I will see the biggest challenge is on the organic side, because then the molecules might be damaged with the laser. And that's why we have to think about, okay, if we have a laser source that resonates with the frequency of the molecule, will that be the right way to do it? And that's the flexibility we are searching here.
Very good. And some of the methods have, to an extent, been established, as you said. Why is this possible to achieve only now? Why would this project be possible?
Yeah, so the methods are established in terms of, you mean solution process and thermal co-evaporation?
Yeah, especially with the evaporation methods, with the hybrid systems.
Yeah, absolutely. So compared to co-evaporation, the difference is that in co-evaporation, if you go for very complex composition, imagine again 5, 6, more than 7 elements, you need every time a different source because you depend on the volatility. So you have something very volatile or not, you need 2 different sources, and then it becomes a very complex system. So what we want to do is to reduce the number of sources to a minimum of 2, or maybe just a single one.
Thank you for clarifying. That will be all from me. Thank you.
Thank you so much. Now I see Sara.
Hey, Monica, can you please comment on the growth rate that you expect from your technique, both for the organic and inorganic material, please?
Yeah, sure. So also there's another motivation to use lasers, because when you have lasers, you can also play with the frequency. So we have a pulse laser. So you can go, it depends on the laser we will get, but normally they go up to 50 hertz or 100 hertz. And if you work, then you can work from 1 hertz to 10 hertz to 20 hertz. And the frequency of the laser basically defines the amount of material we're taking out and the reposition rate of the film. So that's also the idea here, is that we can go and test different deposition rates. An estimation is from 10 nanometers per minute to 100 nanometers per minute, roughly.
Can you compare with other techniques, please?
Absolutely. So thermal co-evaporation at the moment is also 10 nanometers per minute.
Okay, so you aim to achieve similar results of the
absolutely.
state of the art.
Yeah.
Okay, thank you. And the other question is on the cross-contamination. So in the same chamber, you will have different material. What are the mitigation for cross-contamination issues?
Yeah, that's an excellent point. Cross-contamination is a known issue for all the vapor depositions. So we have to optimize our targets, and that we know that, I mean, first is in the design of the chamber so that the two targets can be separated enough. I mean, this is also something that is done in co-evaporation. I believe we can solve it with the good design. And then on the chamber, we have to consider all the things that are in the chamber that will go to the thin film. So we need to really control that the chamber only have the sources and nothing else in the walls and so on. So of course, I mean, then it goes on the management of the system in terms of cleaning and so on. But it's important that the only source of the precursors is in the targets. And then do good calibration, of course.
Thank you so much. Now I see in line Lynn.
Okay, hi, thank you. Hi from the fourth floor, Monica. I wanted to ask you some more details about your work plan for the bismuth-based perovskites, because I was a little bit confused by this. Bismuth is not isoelectronic with lead, and so you would need different stoichiometries or compositions for bismuth-based perovskites, right? So what's your strategy actually for finding these compositions?
Yeah, that's an excellent point. We were motivated by recent works published in the literature, different groups actually from Stanford, and here bismuth have a different oxidation state to make basically the neutral structure. So we will have to first, we don't control the oxidation state until they form the thin film, and then we will need to do analysis. Our motivation for bismuth was mainly based on these these papers that came out, and from there started screening different compositions. And the motivation is that, again, because bismuth is highly volatile, we can show this versatility. And I mean, the field is highly dynamic. So we will see very soon if actually it's a very promising material or it's just a very interesting dopant and so on.
But can you clarify your motivation a little bit more? Is it that you want to make more efficient solar cells then? Because bismuth doesn't seem right now to be one of the most efficient materials, or is it more about the stability or more like a proof of principle of the method?
Is actually the proof of principle of the method to show this full versatility, because it's a very difficult compound to grow. So we are not targeting here record efficiencies solar cells. Our motivation is if we have this system that is so versatile, we can move on to material discovery. And material discovery means we need to be very versatile with compositions, and bismuth will be one of the demonstrations that we can go even beyond lead to something much more complex.
And then maybe my final question, I don't have to tell you that the perovskite field is extremely competitive and dynamic, as you said yourself, and you're coming from a different field, the TCOs. So how will you survive in this field? What's your competitive advantage?
Yeah, that's an excellent point. Indeed, I have been working with transparent conducting oxides, fully inorganic materials, but I actually think this also brings the benefit in the project. I'm coming from taking a different perspective in terms of growth, and then proposing what is a physical vapor deposition technique that is used already partially in silicon, for example. So if we learn from the PLD, we can also move to sputtering deposition. And I think having this vision of what is already kind of established also in semiconductors to take it to the perovskite field that has been mainly focused in solution process and chemistry and so on, is kind of bringing a new perspective. And then I think the ERC will allow me to see also what the reaction of the community is on this type of new methods, which I think is highly needed to, diversify a bit more from the co-evaporation in terms of dry deposition.
Okay, thank you very much.
Thank you, Lynn. Now, Wolfgang.
Yeah, thank you very much. Monica, I want to follow up here a little bit. You stressed a lot that the versatility is key, one big advantage. But can you comment a little bit on the limitations? Can you make any kind of 2D perovskite layer? What kind of cations can you really use? Do you really get such layers, or what are their challenges?
Yeah, that's a very good point. But there are a lot of challenges. I mean, there's always challenges, right? So we don't know, we cannot predict now what is the library of molecules we can deposit at the moment. And that's why, I mean, we are taking the idea here of this, what we call here organic material, which is the target on the left, which the idea is that you put all your molecules in a matrix, which can be methyl glycol or something. And the laser is actually evaporating only the matrix, and then the molecules are released. What is the challenge? That the molecules will go up in your substrate, but then they will fill the chamber as well. So how do you control the rate that they attach to your substrate? And another challenge we have is that if you put some temperature in your substrate, they come and they leave. So the sticking on the substrate will be something we need to study with really a lot of detail. Because molecules are very volatile, and in vacuum, volatility will be higher, so they might come and leave. I think it's more that, and of course, we need to also confirm the integrity of the molecules, and that means we need to do, for example, NMR to make sure that things are going there and that we are not breaking the molecules. It's part of the research, I think.
Maybe another question. Because as I understand, you also want to make rather new materials. You want to screen materials, so materials which maybe are not accessible by solution processing. But at the end, your milestones were always the around 15% solar cell in your proposal. So how do you tackle this issue of first you need to develop the process, you need to somehow make sure you make the right material, and then you also need to embed it in a solar cell, which is a completely different challenge. And then you measure, let's say, a low efficient solar cell. How do you then address this issue? How can you find out what was the problem? What kind of reference can you use?
Yeah, this is an excellent point. I mean, we put some target kind of base efficiency because, I mean, at the end, the functionality is very important. So material science, we go for synthesis, structure, property, functionality. So we needed to prove this. We put a 15% to be conservative to what is actually kind of a state of the art, right? That is beyond 20%. And here, I mean, for solar cells, I have to admit, I'm also relying a lot in our collaborators that because we know that making a device is not straightforward. So we want to have the material and show, okay, is the functionality there? But then we need to have the right contact layers and so on. These devices are going to be small devices. Basically that's to have some target to say, okay, if you go above this 15%, I mean, it's going to be very promising. Otherwise, it's not. And so that I'm relying with the device experts as well, our collaborators that have shown very, very high efficiency devices.
Just as a follow-up, you said you want to check whether the functionality is there before making the device, which makes a lot of sense. What kind of functionality do you want to
so we do a standard characterization. So we have photoluminescence and photoluminescence quantum yield, for example, that we can do. And as a synthesis or material science, I mean, we will do first a lot of structural characterization as well, and link this mainly to PL absorption. And I think that will be one of the first. If we can do conductivity measurements, that also will be very interesting, because then we can correlate to the synthesis. I mean, synthesis and the microstructure at the end. And then if PL is okay, absorption is okay, thickness control is fine, then we can move to devices. And of course, we need to grow in contact layers such that the substrate is the right substrate as well.
Very much.
Thank you. And now the last questions will all come from Ina. Ina, thank you.
Okay, yeah, thanks. So I have one question about your competitors. So you're for sure not the only one trying to grow these nice films. So who are your big competitors and how do you set yourself apart from them?
Yeah, that's a very good point. I mean, as I put in the state of the art, there are very few groups working on pulse laser deposition of halide perovskites. Of course, we are not the only ones proposing this. It was proposed at Duke University, one type of method, and in Japan, another method. But the difference is that when people that is proposing this is not in the solar cell field, so there is a large discrepancy. And in terms of BAPE or the position, of course, there are key leading groups on this, like the group in Valencia, Professor Hembolink, and I'm in close contact with him because it's going to be very interesting when we, for example, have our first films with laser deposition and we can compare to co-evaporation. So that I don't see as competition, but actually very good to learn from each other when we do full dry deposition. And in PLD, yes, it is a very well-known method for oxides, but for halide perovskites, it's really very, very few groups doing this.
Okay, thank you. And I'm also wondering about how you want to really create defect-free films. So does that not also depend on the temperature of the target and like humidity or things like that? I mean, under vacuum, you're not so flexible in changing the conditions of the growth. So how can you ensure that it's defect-free?
Yeah, so there are different strategies. Actually, in the vacuum, we have a lot of parameters to play with, as I mentioned, because just using the laser means you use different laser fluence, different frequencies, where we can control the growth rate. Then we can also play with the substrate. So we have a high, let's say, very large parameter space for the growth. Also the base pressure and the working pressure on the system that is controlled with argon, that's also going to be a very important parameter to play with. So, I mean, we do have this part. And in the third work package, I'm proposing the growth of epitaxial layers, which is one of the strategies to go for minimizing the effects in the films, where you grow as crystalline as possible and as single-oriented as possible films. That will be one of the main strategies to go for defect-free films. But of course, I mean, this is what we aim for, defects. I mean, we can think about all different kind of scales of defects.
Okay, thank you.
Thank you very much. And with this, we close the session. So thank you so much, Monica. And now, after closing this mock, maybe a couple of minutes for telling us yourself, Monica, what are your impressions or maybe some tips and tricks for new applicants?
Yeah, well, thank you for this. I actually first have to say this presentation was from 2019. So I was really, so the presentation, I missed one slide. So sorry for those, because it was 5 minutes exactly when I practiced, but as you could see today, I was not that ready.
Don't worry, it was perfect.
But yeah, so for my case, it was 5 minutes, so it's much faster. And yeah, I mean, I think the short answers is important. And I mean, I think the questions you asked were very relevant. Normally, you want to know what is the challenge in the field, who are the competition, and so on. That's what I feel. So I think most of you ask questions from the reviewers, which was similar to what I got during the interview, actually. It brought me back to 2019.
Perfect. Thank you so much. Maybe I don't see any question in the chat, but maybe there are something that anyone from the participants want to ask before we close the meeting. Or tips from the panel as well.
I think one important tip to share is also that sometimes when you apply for these things and then you present or you get questions, it's good not to feel threatened. Like people just, we are all scientists and, it's always good to don't feel like you're trying to kill. I think the panel is never there to try to kill a proposal, but actually to see how the science comes out more and more. And yeah, I think that's also an important thing.
I agree.
Yeah, and maybe if you feel like it went really poorly, you're not the best judge of that. So sometimes you may feel, oh, I didn't answer this well, just wait for the results. And, you can't necessarily tell what the impression of the panel was, and just be patient, wait for it, and you will hear the results relatively soon.
I agree. I also feel a tip for everyone that will have to prepare mock interviews when they are called for the interview. It's good to really prepare mock interviews in this way, like on Zoom or actually even WebEx directly. That is what ERC use, and ask everyone to really act as if it was the mock interview, because it helps. It's a bit of an alienating experience to connect online to do it, and it's good to prepare in the same setting before.
Yeah, I think practicing the change of slides, which is the problem I had. I just went and I couldn't change, and then it went through and I skipped one. So I think practicing the change of slides and the full setting online to be really ready is important.
True. Okay, if there are no other comments, then I would once more like to
There's a question in the
yeah,
chat,
of
right?
course. Thank you.
I think there's something.
So, I would like to ask if there is any dress code. I have to say, so in my case, I was not advised any dress. I dressed in a formal way. I was with jacket and shirt, but I was never advised anything. I guess in general to be formal is a good thing, but I don't know if anyone has any tip.
I think whatever you feel comfortable and confident helps.
Yeah, I don't think the panels really care too much about that. So important is, of course, a good microphone, and so that you're audible well. I did the interview in person back in 2017, and now that we're on Zoom, it's like the camera should be relatively good, but especially the audio, you really need to hear them well and be very clear and audible. So if you don't have a good desk mic, maybe borrowing one. Some Apple AirPods are pretty good for audio, so make sure that you're well understandable.
Yes. Also lightning. Don't do what I'm doing now. This is bad for your face. But it's just my microphone is broken now.
It helped me also, I think, backup slides. So at a certain point where they're asking many questions, as I was flipping with the numbers of the slides in between one and the other. So I think also it helped because you have also images that are helping the commission to see also what you're explaining.
True. And one tip I learned from a friend that got ERC before is very cool. Also in PowerPoint, you can put links within the document so that you can connect very quickly if you go through the slides back to the initial one. So you can use link within the document to go quickly between all the slides. Maybe there are questions? If not, let me thank once more the two interviews to go through again the experience of the interview and all the panel members for their time. Thank you all so much and finger crossed for everyone that is applying. Bye-bye.
Good luck.